of doing that. Okay, so we have been talking about reaction orders. So just to kind of remind you how that goes, we're focusing on how fast a reaction occurs. And specifically, we're focusing on the initial reaction rate for now because we know that reaction rates get slower over time, is equal to the rate law constant K. Now, if we have A plus B going to form, I'll just put P for product or products, then the rate law expression would go like this, where it's the molar concentration of A raised to its reaction order times the molar concentration of B raised to its reaction order. Yep. And we said that these reaction orders, M and N, can be positive, negative, whole, fractions, you know. But literally, they are saying how the molar concentration of the reactants affect the rates. Okay, so we did it by inspection on this is Wednesday, on Monday. Okay, but that's, I wish life were always that easy. It's not. We're going to do an algebraic approach. How do you get to these powers? Okay, and that's going to be because the reaction order might be 0 or, well, I guess if it's 0, it's pretty obvious because you change the concentration of the reactant and it doesn't have any effect on the rate. But the reaction order could be first or second, but if you don't double it, you don't see that doubling and quadrupling for first and second order respectively. So, all right, you're like, well, why didn't you just set up the experiment that way, right? So we're going to look at this example. We're going to run this trial twice and look at how changing the molar concentration of the two reactants, what it has on the effect it has on the reaction rate. So the first time we ran it, we have the molar concentration of Q, 0.170 molar, R, 0.233 molar. We run it a second time, and notice on purpose, we kept our molar concentration the same. So notice that we do see a difference here in reaction rate. Not so surprising, we increase the molar concentration of Q, we increase the reaction rate, but we don't know what the reaction order of Q is. Okay? We can't, with this data, as far as I can tell, get to the reaction order of R, but we can of Q. Down at the top or whatever, if you want to, kind of along this vein, we could say that the reaction rate is equal to rate law constant, K, times the molar concentration of Q, raised to the M power, which is reaction order, times the molar concentration of R, raised to the N power. That's kind of what we have going on here. So we are going to get to it through logs. I can't remember, Ren and Stimpy, you guys are too young for this, but on Nickelodeon used to have a cartoon, Ren and Stimpy, and they were really goofy. And I can remember one of the things they would celebrate is getting a log. I say, it's log, it's log. It's a commercial for a log, I don't know. But whenever I think of the logs or logs in general, like, log is log. But we are actually going to use what logs can do for us. The law of logs are kind of summarized here. Now these are all log base 10, but it could be the natural log too. We're going to use that to our benefit. And I'll show you how we're going to do that to get to, you know, you need to use logs, and actually we'll be using logs when we talk about pHs, okay? But if you want to get to a power, they're powerful. I'll kind of show you how this works. Okay, so in this example, we're going to look at the two trials we ran, but remember R was constant. So remember what we did with that before. We basically balled the, well, it's going to cancel here in a minute. So R is constant. So there is an important thing that we do, especially in Chem 2, to kind of manipulate data. We can go ahead and say that for that second trial, we'll go ahead and slap up a number 2 subscript there. For the second trial, the rate is equal to the rate law constant Q times the molar concentration of Q at the second trial raised to M. Molar concentration of R, the second trial raised to N. We're actually going to go ahead and divide, basically rate 2, we're going to divide rate 2 by rate 1. If that's the case, then the quantity on the right-hand side, we're going to divide by each other. Okay? So the beauty of all of this is that this quantity over here, I know it's kind of grayed out, but hopefully you can see it. Do you guys buy this? That in this quantity, the K's are the same, and actually the molar concentration of R did not change. So by golly, that darn thing goes away. We don't care what N is. Okay? This little exercise we're doing right here is to get to the reaction order of M, period, exclamation point. Okay? So we'll go ahead and rewrite that. Okay, so we could say that the ratio of the rate 2 to rate 1 is equal to the ratio of Q2, molar concentration of Q, for the second trial to the first trial, all raised to the reaction order M, and we're after M. So here comes one of our first use of laws of logs. So we can take the log of both sides, and I think we're going to go with base 10 here, but wouldn't have to be. We can take the log of both sides. The cool thing about this, taking the log of a quantity raised to the power is equal to basically that power times log of that quantity. So that would be, to me, it looks like the third line over here on the right. Log base b of x to the n is equal to n log of x. That's exactly what we're going to do. It's a beautiful thing. And we have just kind of flattened out m. Now it's just, to me, normal algebra. It is totally normal algebra. Don't let logs throw you off. You have an LOG key. Okay? So I can rearrange this solving for m. And sometimes, I know on my answer keys, I rearrange it, and sometimes and then plug in, and sometimes I plug in and then rearrange it. So it just kind of depends on what kind of mood I'm in. But bottom line, we can get to the value of the rate law constant, or excuse me, not rate constants, the reaction order of Q by taking log of the ratio of rate 2 to rate 1 by the log of the ratio of molar concentration of Q2 to Q1. And we have real numbers for those. Is that not wonderful or not? Okay, so we plug in those real numbers, snag the rate 2, rate 1, plug them in, snag the Q2, Q1, plug them in. Now, if you're like me, this is kind of like balancing your checkbook, and if it's really important, you do it multiple times to see if you get the same answer. Okay. There are a couple different ways to work this. I can't remember how my answer key does. Oh, what my answer key does is just to kind of distill what that ratio is, plug it in. Okay, so we have the log of two numbers. Which is 2. You're like, really? Yeah. All that's to say that the reaction order of Q is 2. That's it. That's an algebraic approach. It is a classic. Okay. So 11 was due today, and let's take a quick look at 12 and 13. And they look like oh, come on. Where it should be. Well, I'll find them and put them out there. One more time, 12. There. Oh, okay. So this is 12. Okay, so we have 2 reactants going to form products. And let's just kind of show you my hints, because I thought through it at my desk, and after I thought through it, you know, and you may use this, you may not, I don't know. But one of the things I first start out is I usually write this generic reaction rate, and just because I can, and it gives me warm fuzzies. Of course, that's not the rate law expression, but we're trying to come up with the rate law expression. Okay, so if we focus on experiments 1 and 2, notice that B is held constant, so we can actually get to basically what M is, the reaction order for the reactant A, just like in class. Okay, and now I said, why don't you go ahead and use, I said 2 and 3, but it's going to be a little bit confounded because your molar concentrations of A do not cancel out because they're not the same. But now you know what power to raise A to, okay? So it's a little hairier than we did in lecture, but it definitely can be done. And then remember, last but not least, whenever you do a problem like this, you should go ahead and knock out the K value, find M, N, and K. Remember, you can come up with the rate law constant, K, for anything once you know M and N. So basically, you pick one of these 3 trials and go back now and plug in the molar concentration for that trial and the reaction orders, which you now know, and of course the rate is the last column. So you can get to K. And then the second one looks like this. Again, I would write the generic rate law expression just to remind me what I'm after. I said it's easier than 12. The reason for that being, we do kind of have for your homework for 11, remember we had kind of a doubling. If you double here, which is what we're doing here, actually you see, I think it's a doubling here. And that means it's what, first order? Okay, so you're back to by inspection for at least for the reaction order with regard to what, the Cl2? Okay. But then you have to go back and since it's non-systematic, no, I guess it's systematic for 1 and 3 because you're holding Cl2 the same and you're doubling NO. And I think you come up with a quadrupling, which means reaction order 2. So that's kind of nice. So this one actually is kind of back to what you did for 11. And that's all I got for that. Okay. Oops. Okay. So, coming up with those reaction orders, and actually all this data is, I should emphasize, it's all initial rates data. That last column, initial rates. We know that the rates are going to get less over time, slow down over time. Initial rates data. So one other way to do it is graphical approach. And actually, a few things I talk to my husband as I do sometimes at break. And actually, this is what you're doing in lab tomorrow. So pay attention for your lab write-ups. This is what you're doing in lab tomorrow. The other thing is that you'll notice there is no homework questions over this, and this will not be on your test. You're like, all right, so why are you doing it? It's no homework questions, not on your test, because there is a lab tomorrow that you're going to be wanting to get a 10 on. Okay, so this is just another way of using initial rates data to get to the reaction orders. Okay, so here we go. What if we have 2 reactants, A and B? And remember, the lowercase a and the lowercase b are the stoichiometric coefficients of the reactants, which are not the reaction orders, by the way. You know, red, bold, blue font, unless it's an elementary step, which we'll talk about at the end. Okay. So you only get to the reaction orders by experimentation. So this is the generic rate law expression for A and B reacting. Okay, we're trying to get to the rate of it. So let's go ahead and take the log of both sides. And I'm going to show you something that we can slap up on a graph and look for the slope of a line. So now, of course, this isn't log base 10. This is a natural log, but it still follows the same rules. If you, kind of over there on the right, if you take the log of a product, can you see where this is a product? You have the natural log of K times the molar concentration of A raised to its reaction order times the molar concentration of B raised to its reaction order. We have 3 terms over there. You can actually break that out into adding. Let's see, which roll is that? Log of, yeah, the first one. Yep. Okay, and we're going to break it out. I'll show you how we're going to break it out. So tomorrow's lab, and actually for this exercise and the way this works is, basically, we're going to run 8 trials, 4 and 4. For the first 4 trials, basically, we're going to hold B constant and vary A. And for the next 4 trials, we're going to hold A constant and vary B. Okay, and I'll show you why that works. So in this case, if we're going to hold B constant, we're going to go ahead and slap B over there with the K, because that's the rate log constant. We'll put the constants together. So remember, A is going to vary here, so this is of interest. Now remember, if you take the log of anything raised to a power, it's equal to that power times the log of. So voila, we are very close to having something that we can plot. Okay, so the natural log of the rate, initial rate, is equal to the reaction order, M, which we're trying to get, times the natural log of the varying molar concentrations of A, initial molar concentrations. And this thing is constant. So if we go ahead and plot along the y-axis the natural log of rate, and if we plot along the x-axis the natural log of the molar concentration of A for our 4 trials, then actually it's going to be a positive slope, okay, and that slope is going to be equal to your reaction order. This is kind of funny. I never thought about it until just now, but of course, you know, we're used to seeing M as the slope, but actually it just so happens that M we've also picked to be the variable for the reaction order of A. Just kind of worked out that way. But that's how we do it. Okay, so this kind of reminds you of that first one up here. Law of logs, it's logs, log. Okay. Okay, and the reason we went this route is because we held B constant. We just kind of threw it over there, kind of the constant of integration or whatever that thing is, the y-intercept. So yeah, I'm going to show you an example, but kind of if you're a visual person, you know, this is what it looks like. This is the natural log of the rate, and this is the natural log of the molar concentration of A. Why? Because we varied the molar concentration of A. And it should have a positive slope, and the slope, M, the slope will be equal to, I'll just put Rxn order, reaction order. Not to say M is equal to M. You're like, duh, M is equal to M. Okay. Cool. Well, we're going to do a very similar thing with our second set of 4 experiments, but we're going to vary B and hold A constant. And in that case, we're going to go ahead and stick the molar concentration of A over with the rate log constant K. And then we're going to focus on here, we're going to plot what? Along the y-axis, again, the natural log of rate, and along the x-axis, we're going to plot the natural log of the molar concentration of B, which we're varying. The slope will be positive, and it will be equal to the reaction order of B.
This might be a dumb question, but these going to be 2 different
2 plots. You're right. 2 plots. You're right.
1 graph, 2 plots.
Let's see. 2 different plots.
So just 2 different
They'll be,
graphs.
yeah, 2 separate. To me, a plot is a graph. So lines. The lines will be on 2 different graphs. Graph here, line. Graph here, line. And the titles will be getting to the reaction order of A, reaction order of B.
And that's because you're holding one constant the same, the opposite constant.
Yes. Yep. So just to kind of emphasize that, if you drew this on the previous one, look how this is different. ln of rate, and now there's something different along the x-axis. It's not the ln of A, now it's the ln of molar concentration of B. They cannot be on the same graph plot. They can't be on the same scale because they're different scales. So I hope that helps. Yeah. Positive slope, slope is equal to M is equal to N. All right. But wait, this is the coup de grace. There's one more graph. You're counting graphs, just there'll be 3 graphs from tomorrow's lab. The last graph actually you can knock out K with all 8 trials. Now this will be a 3rd graph, a 3rd plot, with 1 line. Each plot has 1 line, 3 plots, 1 line each. Okay, so here's how this would work. If we go back to kind of our rate law expression, rate is equal to the rate law constant K. We're after K. times the molar concentration of A raised to its reaction order, which we know, times the molar concentration of B raised to its reaction order, which we know, so we know M and N, okay? So this one, there's no natural log required. Just simply, if we go ahead and plot rate along our y-axis, now this, I know it's just, okay, over here there'll be rate, not the natural log of rate, but rate here. And then along the x-axis, we are going to take basically this quantity. So along the x-axis, for each of your 8 trials, you're going to take the molar concentration of A raised to its reaction order, which you know, times the molar concentration of B raised to its reaction order, which you know. That's it. So for actually the example I'm going to show you, you're going to see 8 points, and they're kind of clustered, I think, is what they usually are. Kind of like 4 sets of 2. Okay? And in this case, just like this kind of looks like, now M, your slope, will be equal to your rate log constant K. Isn't that slick? Oh my gosh. But again, there won't be one on this test, and there's not a homework. This is exactly what you guys are going to do tomorrow. What I think is fun that you're doing tomorrow is that you're actually getting initial rates. So you'll be using, I have some stopwatches. Somehow you want to kind of time it, an observed end of the reaction, or beginning of the reaction, end of the reaction, I guess, at the same point. The lab quests also have timers. Yep, that's it. Now, this is one of those things where it's easier to kind of show you, or it helps to show you. So here we go. You're gonna see 8 trials, basically split in 2. And the first set of trials were varying NO, holding O2 constant. The second set of trials were holding NO constant, varying O2. Here we go. So you see the blue line there kind of separates the 2 sets, okay? And you see where O2 is held constant there, NO is held constant there. So I know one of the things I was going to do. On the previous slide, I told you what I'd like to do because it gives me warm and fuzzies, is I would probably write rate is equal to the rate log constant K times the molar concentrations of each of the reactants. In this case, we have 2 reactants. We have NO raised to its reaction order M, and O2 raised to its reaction order N. That's what I usually would do. So as I've written it there, can you see where these first set, since we're varying NO, we're actually going to get M, the reaction order of NO, and here we're going to be able to knock out N, the reaction order of O2. So here we go. Let's see what those look like. All right. Now the temperature is mentioned here because we will be talking more about this actually today, getting to it a little bit today and Friday. But your K has different values depending upon the temperature. So it's important that these are all held at the same temperature. So here we go. Here's the first 4 trials. We increase N, and our rate increases like you would expect. So remember, we need to get the natural log of each one of them. And we're going to put the natural log of the rate along the y-axis, the natural log of the NO along the x-axis, and see what we got. If you're kind of familiar with logs already, you guys know that if it's less than 1, when you take the log of something, that number is going to be negative. If it's greater than 1, the log is going to be positive. Okay, so we let logger pro do the heavy lifting. And that's a nice straight line. Those are those 4 points of the natural log of the rate versus the natural log of the molar concentration of the NO. Pretty good. And we said that the slope would be equal to the reaction order of NO. Okay, now here's sometimes where students say, well, how do I know it's close enough to round up or round down? Well, I'd say, 1/100th is close enough. I'd say, but experimental data should be pretty good. So if you're more than I don't know. I thought about it, but if you're more than 0.1 either side, probably it's not an integer. Because remember, reaction orders don't have to be integers. So, all right, there's that one. Let's knock out the next one. So we'd say it's second order with regard to NO. And this is the other set where we are varying now the molar concentration of O2 increasing. You can see that the reaction rate increases, which makes sense. Take the natural log of both of those, and we're going to go with natural log of the rate along the y-axis, natural log of the O2 along the x-axis, and see what we got. We're pretty good. The slope here, okay, slope is 1.02, first order. Okay, very good. And then the coup de grace is to knock out the rate law constant K using all 8 trials. Okay. So the rate law expression, not finding the exact value for K, rate is equal to K times the molar concentration of the NO raised to the second power times the molar concentration of O2 raised to the first power. Okay, so the overall reaction order is 3. So setting ourselves up to find the value of K. So this is our raw data. Now this, the column here, okay, to find what you plot along the x-axis, you're going to have to raise the molar concentration for each trial of the O2, of the NO. You're going to have to square that and multiply that by the molar concentration of the O2. Again, let LoggerPro do the heavy lifting. You can go ahead and pick cells that you want to manipulate in that blue column. That's a calculated column. Okay. All right. So let's see what those 8 points look like. So again, you're going to see rate along the y-axis, and then that blue column, that calculated column, along the x-axis. So here we go. There's your 8 points. So the numerical value that you find for the slope will be your value for K, your rate law constant. 7.1 times 10 to the third. Okay. Units of K, we talked about this on Monday. Units of K, the way I think of it, have to kind of cancel out what your overall units that you introduce when you raise, in this case, molarity up to the power of 3. Because your overall reaction order is 2 plus 1 is 3. Okay, so I just have to think through it. And we kind of did it for 0 overall reaction order, 0, 1, and 2. But if this is 2 and this is 1, okay, and your initial rate needs to be moles per liter per second or per time, okay, that's where you have moles per liter squared, moles per liter, and so that's why you have to introduce moles per liter squared down here. Okay? And actually, we can kind of unpack moles per liter, and that would be liters squared per moles squared per second. So that will be the units for K if your overall reaction order is 3. Welcome to Chem 2. Messy, yes. Doable, yes. Okay. So, again, the value is 7.1 times 10 to the third. We got that from the slope. The units will be liters squared per mole squared time. All right then. Just to kind of remind you, or actually, I remember this. Okay, so yep, up here on the slide is kind of what I did over there. Rates are always going to be changes in concentration. Molarity is a great one. Moles per liter, change in concentration per time, so moles per liter per time. And so that kind of blank there needs to cancel out what we introduce when we raise the molar concentration of NO to the second power and the molar concentration of O, oxygen, to the first power. So that's it. There's a lot of things in physical science where I don't memorize things because I'm bad at memorizing. I just kind of put the pieces together when I need to. Okay, so there is no homework, but hopefully you guys are set. Pre-lab should be a breeze tomorrow. So let's look at, like I said in my slide, I debated, but I think we really should jump to part 5 for a couple of reasons. One is jumping to part 5 instead of going on to part 3 will kind of clear our palette, because parts 3 and 4 actually introduce some more graphs, and I'd rather not do that. And part 5 is important. It's all important, but part 5 is going to set us up for actually next week from Thursday. We are going to do all part 5, yes. I think on my slides I said we're going to start part 5 today. We're going to finish part 5 on Friday. Yeah. And then we're going to go back and pick up parts. His parts. We'll go back and pick up parts 3 and 4. Then go to part 6. All right. So, you guys remember, do you guys have this slide? Yes. Good. We said, how fast does a reaction occur? Well, gee, I don't know, okay? But just common sense, and we looked at some videos, common sense means that somewhere in how fast a reaction occurs, the reaction rate, we have kind of these general factors. Now, I'm not putting a number to them yet. But we said that, for instance, they need to collide, and they need to collide with enough energy to proceed from reactants to products, and oftentimes there is an orientation that they need to collide with sufficient energy. So it's like, when I look at those videos, I'm kind of like, it's surprising that any chemical reactions ever occur. But they do. It's all about electrons. So anyway, how fast will a reaction occur? And honestly, I'm going to go to this collision frequency, and to me, that deals with concentration. And to me, when I look at the rate law expression, to me, this really screams concentration. I mean, as we've been talking about kind of the rate law expression, the more concentrations of the reactants raised to the reaction order, that's collision frequency. Well, that leaves 2 factors we need to talk about, and those 2 factors are kind of balled up into the K. Okay, so balled up into your rate law constant is something with regard to energy and also something with regard to orientation. I actually called Dr. Snipes, my husband. I'm like, now is this why, when you look in your textbook, the Arrhenius Equation is what this is called, actually, and I'm a little embarrassed because you know how much I complained about K's? In Petrucci, and a lot of chem textbooks will actually use an A for that K sub 0. Okay, so where I see K0 as, K0 is going to be your orientation factor, a lot of times they'll put an A for that. Okay, so actually the first K is this K. That's your rate law constant. So your rate law constant kind of can be broken down into your orientation factor, E raised to a power, and that power has an E sub A, capital E sub A, that's your activation energy. Of course, you guys know what R is, it's the ideal gas law constant, and T is the temperature in units of Kelvin, the absolute temperature. And it's no small thing to notice that the Arrhenius equation, what this is, the Arrhenius equation has E raised to the negative power, E raised to the negative activation energy over RT. Okay, so this is kind of what's going on with this K. So we're going to actually pick that apart and double check that we have both an orientation factor and an energy factor, which we do. Okay, so the K0, the orientation factor, that's the only thing that has units here. Because otherwise you have e raised to a negative power, or e raised to a power, which is unitless. So the units of K0, the orientation factor, will be the same thing as the units of K, which is your rate law constant. So E, I'll go ahead and write the Arrhenius equation here. And you will have, dare I say, an equation sheet for your Unit 2 exam, good, bad, or otherwise. You can ignore it if you want. Okay. So what was I? Oh, yes. So this up here needs to actually cancel with regard to units, and it will if you go ahead and make the activation energy kilojoules per mole, and if you make the temperature Kelvin, of course, and make R kilojoules per mole Kelvin. Like, are you sure? I'm like, yep, Kelvins will cancel. They'll have kilojoules per mole. That makes it unitless. That works. Again, in your textbook, and if you're kind of researching this, the orientation factor actually is a capital A. So all there is the orientation factor. And I don't know if it's exactly this simple, but we talked about the effect of a catalyst will always increase the rate, the reaction rate. And to me, when I think of a catalyst, I always think of orientation. But I think actually when we talk about, we're going to have I have a slide on what does a catalyst do, and it actually has an alternate mechanism kind of behind the scenes, and we'll get to that. But all right, so if K0, or the orientation factor, fixes orientation, then we can actually see that this E raised to the negative EA over RT, that actually is our energy factor. I brought my calculator. I don't know if we're going to do an example here. I know we're not getting to homework. But everybody's calculator has E raised to the X, and that's exactly what you're going to be using. It should be in conjunction with your LN key. See if I can find mine. Every calculator is different. Oh, I found it. It threw me off because my ln was capital L, capital N, and then my shift for ln is actually e raised to the x power. So that works. Did you find yours?
Mm-hmm.
Okay. Well, trial and error. Okay. So this EA up here, this activation energy, let's look at it a little bit closer. I have some energy diagrams. It's kind of cool. I think it's exciting because we've talked about endothermic reactions where basically it takes energy in, and exothermic reactions where energy is released. But both types of reactions have what we call an energy barrier, and that's the EA, that's the activation energy, that they need to overcome in order to, what we say, proceed, I like that word too, proceed from reactants to products, that's the energy barrier. And you can see this on these energy diagrams. It's to hump. And I don't know if it'll make it to this Unit 2 exam, but I love putting energy diagrams on Unit 2 exams and Chem 2. So. Okay, so here we go. This is an exothermic reaction, so we know that actually that means energy is going to be given off, so our final energy is going to be less than our initial energy. So that's the energy of your reactants and products, or sorry, that's your energy of your reactants. Okay, you see the hump? That actually is your energy barrier, okay? Activation energy. So we've talked about delta H's. That is your delta H. That's your their heat of your reaction, and it would be negative. Exothermic. That right there is your activation energy, your energy barrier. And they're always positive. Okay, cool. So that was exothermic, energy is given off. Endothermic, energy is taken in. So that's why actually you're going to see that in your final state, your products actually have more energy than your reactants. Okay, here's the hump. Whoop. There's your products. Okay, we could come up with the enthalpy of the reaction. It's final minus initial, so it would be positive. It's definitely endothermic. And then from here, when we come up with the energy barrier, the activation energy, again, it's from the initial state up to the top. So that's your activation energy. You can say a lot with a picture. Okay, so that was pretty generic. Let's look at N2O reacting with NO. Okay, so on the reactant side, okay, looks like it's going to be, an exothermic reaction, as it's written from left to right anyway. Okay, the products, kind of a visual of those. Delta H of your reaction, negative 139 kilojoules. Your activation energy in what we call the forward direction. Now, it's only being shown in the forward direction, but I'm going to just take you for a quick detour. What if it went from what we say left, what if it went from right back to left again? What if it went in the reverse direction? In the forward direction, there's your activation energy, 209 kilojoules. We'll talk more about transition state, but you can already kind of see what it is. It's kind of an in-betweener, in between the reactants and the products. Okay, now, if, and it doesn't show it in the equation down there, but if we could take this darn thing and go backwards, because we talked about chemical equilibria recently, okay? In that case, if it was going to go backwards, then can you see where the activation energy would be actually here? Significantly more activation energy required to go in the reverse direction than the forward. Well, I think that's kind of how far I wanted to get today. And we're going to pick it up here with another plot. Let those other plots sink in. Okay? Arrhenius plot. Clausius-Clapeyron plot. Blah, 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 blah.